So in video 2, we derived the quotient rule. In this video, we're going to go ahead and use the quotient rule to find the derivative of a quotient or a ratio of two functions. So here I have a function f of x equals x cubed minus x plus 1 over x squared minus x plus 2. So this is a rational function. It's a ratio of two polynomials. And I can use the quotient rule, which tells me how to deal with the derivative of a ratio of two functions to find the derivative of f of x. So I'm going to go f prime of x. And I do want to recognize that the f of x I see here has nothing to do with the f of x in the formula. The f of x is just standing in the formula as a generic function in the numerator of a ratio. So from a formulaic standpoint, f of x here is representing the x cubed minus x plus 1 in the numerator position, and it has nothing to do with the fact that we named this function f of x. So to take the derivative of a ratio of two functions, the quotient rule simply says take the function in the numerator and take its derivative, and then multiply it by the function in the denominator. So I'm going to take my numerator function right here, and I'm going to take its derivative. So I'm going to take d dx of the numerator function, x cubed minus x plus 1. And then once we have its derivative, the quotient rule says go ahead and multiply that by the denominator function. And then it says minus. Now take the numerator function. So here's my numerator function, x cubed minus x plus 1. And it says multiply that by the derivative of the denominator function. So take d dx of the guy in the denominator, x squared minus x plus 2. And it says divide all of that mess. So fraction bar goes under everything in the numerator. Divide it by the square of the denominator function. So take the denominator function and square it. And now it's just simply a matter of taking the derivatives, the needed derivatives in the numerator, and then cleaning things up a little bit. So d dx of x cubed minus x plus 1, take the derivative of that polynomial. So x cubed, we can apply the power rule. So the 3 will come down into the coefficient position, and we'll decrease the exponent by 1, minus the derivative of x, d dx of x is 1, plus d dx, take the derivative of 1, but 1 is a constant, and we know that the derivative of a constant is 0 from the previous homework assignment. Now rewrite the second function, the x squared minus x plus 2, minus, rewrite this function, x cubed minus x plus 1, times, take the derivative d dx of this function, the derivative of x squared, use the power rule, bring the 2 down to the coefficient position and decrease the exponent by 1, so x to the first, minus the derivative of x is just 1, plus the derivative of a constant is 0. And this is all over the denominator. Excuse me. So x squared minus x plus 2, all squared. And then we can simplify the numerator a little bit. It looks like we get just a 3x squared minus 1 here, times x squared minus x plus 2, minus parentheses x cubed minus x plus 1, times the 2x minus 1, all over. That's a horrible fraction bar, but I'm going to live with it. X squared minus x plus 2, all squared. And so here I think it's okay to stop. And so the conversation would be, again, the same conversation we had with the product rule, is when and how much do you need to simplify? You know, how much and when is it okay to stop? So again, just like we said in that video, the previous video, you want to look at it and see if there's any obvious simplifications that can be done, whether they're algebraic or arithmetic. So things that I would be looking for would be whether any of the terms in the numerator or denominator factor, and maybe we can pull out common factors and get things to cancel. Up here, we could combine constant terms, so like terms, so we did that. We could, if we wanted to, multiply everything out, so we'd get, there's 2 terms here, times 3, there'd be 6 terms sitting there, and we would get 3 times 2 is another 6, so we could multiply everything out. It would give us 12 terms, and we could try to combine like terms. But I don't think that's in the spirit of this problem. I think unless the simplifications are fairly obvious, it's okay to leave something like this. Again, the comment that I made before was that usually you're taking a derivative because you want to do something with it. For example, find the equation of a tangent line. And if that's what we're going to need to do, we're just going to need to plug a value for x in and simplify it and get a real number. So look for simplification. Check to see if things will factor nicely and cancel for you. But if they don't, go ahead and stop. And then if you have, if you're questioning yourself, shoot me a message and send me a picture of your work and say, hey, do I need to simplify this anymore, or is what I have okay?